Yeah, this is
Some, yeah.
more news.
Some
It's not even mine.
Is there a second section or is this all one
Yeah, there's a
section?
second section. It's a lot smaller than this one.
Oh, really?
Yeah,
Just because of the timing of everyone's schedules or something?
I guess, yeah. It's usually that way. The second section usually is smaller. But some people have to have that section, and we couldn't fit them all in here, so it's good we have two sections. Okay, it's 11 o'clock, so I have a few announcements to make. First off, you guys need to make an announcement about the SMACS meeting and when it is and all that.
Oh yeah, so our first SMACS meeting of the semester is Tuesday at 5 in that room over there. So
Well,
yeah, everybody should be there. It'll be fun.
okay. I have been working with Morgan Ray, and she has agreed to do a tutoring for this class. So if anyone needs any tutoring, she will be available. Now, I don't know when they've actually got her set up in the system, because when we were talking, she hadn't gone and gotten that part done. But there will be tutoring, and Morgan Ray, I mean, she just, I think she got the outstanding organic student that year or something, which, you know, because she's just really good in organic chemistry, and so I was happy. I tried to get her last semester, but she had other things to do. So she's going to be available Mondays after 10 and Wednesdays after 4, and then she can be available other times, but her schedule goes back and forth on the other days, and so it's going to have to be as per need basis. So if you need tutoring, you can call down to the tutoring center and or whatever it's called, and try to figure out, you know, get it set up or get it set up online for her. And so she's got a lot of tutoring experience. She used to work for Mathnasia over there when they had it, and so she knows how to tutor. And I think if you need tutoring, you'll find that she's just going to be very helpful. Okay, so let's put her to work. Another thing that I've sent out to my advisees, but I usually like to tell the organic classes about it, and kind of probably should have done it earlier. I was waiting for something, can't remember what it was, but you've probably heard from other people about the pre-med internship volunteer program. If you haven't and you're interested in it, this would be more for people who are interested in going into medicine. It's a volunteer, so you don't get paid, but when you go for med school applications, they want to see lots of shadowing experience, and so this has been a good one for that. If you live in Jackson or are going to spend the summer here, you basically go and work from May 27th until Friday, July 10th, and kind of a 6-week program, and you'll go through behavioral health, heart, Women and Children's Center, Kirkland Cancer Center, rehab, and a bunch of other things. So if you're interested, I've got the announcements, which tells you how to go in and get and apply and everything. I think that application ends March 1st, and you have to have an official school transcript mailed directly to the school, and you also need reference letters. So if you're interested in that, if you're pre-med and you're interested in it, what I've heard in talking with Tennessee and students and stuff, what they're looking for is a broad amount of experience. So this would be one good one. Of course, anything is good. I mean, that it has to do with it. This is just an opportunity they have available here in Jackson area. But also, then on top of that, they like to see you also working with individual doctors some. So you have kind of a multiple type of experiences, not just focused in one area. Just having it here in case you're interested, okay? And if anyone is interested in undergraduate research programs, I've had a couple of colleges contact basically I've been mostly with the chemistry. That's, some of them could probably apply for biology as well. So, anyway, have a couple of them that are on my, you can email me and I can forward those to you. They pay during the summer and you do it, you go these various places and they put you up and feed you and give you money. And you do research for them, okay? So it's, those things are also available to students. They're kind of hard to get, but if you're interested, it's worth trying for. Okay, any questions? Well, before we go on, I've had a lot of questions about the 1-4 edition. So if you don't mind, I'd like to just kind of go over it again and how we do it and what you look for. I'm going to take a fairly simple example where we're doing it. Oh yeah. Okay, this is a simple example. We can get more complex if you want to. But remember that we're going to do 1-4 addition. So this is a symmetrical molecule, so it doesn't matter if we start here or start here. So I'm going to number it this way. And what do you want to add? Br2, HBr, HCl, you tell me.
HCl.
HCl, I heard HCl first, okay? Sorry about that. We can do HBr next time if we do another one. Okay, it doesn't matter what else is on this molecule. Okay, nothing else is really going to matter. There is one now that I was working through with someone today, and I was kind of like, well, I'm not really sure, since this would be anti-Markovnikov, if Al wants it or not. So you're never really sure on Al if they're kind of like that. But sometimes you just have to get it wrong, but you got 10 tries. So I would say no, you shouldn't do it that way because it's non-Markovnikov. But, again, who knows? But most of them fell where you had some kind of a symmetrical one. You might have had one that wasn't symmetrical, and then you'd have 4 products, but on this one we're going to have 2 products, okay? So how do we do this? Well, remember it's a 1-4 addition. So we're going to number ours 1, 2, 3, 4. So it's always going to be, your conjugated portion will be numbered 1 through 4 like such. Don't number it this way, okay? Because it's got to be the conjugated portion. So double bond, single bond, double bond. And so you could number it 1, 2, 3, 4, but it doesn't really matter. Okay, so what are we going to do? Well, what's the first thing that goes on? The hydrogen, right? And so we're going to end up putting the hydrogen here. So what's that do over here? Makes a carbocation, right? Okay. Now, when we're looking at that, we could put a Cl here, and that's going to be one of our products. So what we're going to do is we're going to just draw it here with we're going to keep this double bond where it was, and we're going to put a hydrogen here, and we're going to put a Cl here. So if it asks for the carbocation, that's one of the carbocations. And then you put your Cl there. If you had 2 bromines, you put a bromine here and a bromine there, The other thing, this is 1, 2. So always remember, it's 1, 2, 3, 4. So now we're going to do our 1,4 product. Okay, we have this resonance structure. Now let's think about it. There's a p orbital here, right? A p orbital here, and a p orbital here. So resonance, remember, if we have 3 p orbitals, then we can have a resonance structure, okay? And so when we're doing the resonance structure on that, what do? We put this double bond here, and we bring our carbocation over here, okay? That's your resonance structure. So here we are, and we're going to do our resonance structure here. And so in doing that, what we end up with is our double bond here and our carbocation here. Do we still have our 3 p orbitals in the same place? We're going to have our hydrogen here. We do, don't we? So So we haven't moved our p orbitals, we've just had a shifting of electrons. Everyone got that for resonance structure? Okay, so now what do? Well, now where's our carbocation? Down here. So what's our final product? This is for our 1,4. So we've moved this here, so now it's gonna go here. We still have our hydrogen there, but now our Cl goes down there. Are you understanding that a little bit? Any questions on that? This is 1,2 and 1,4 addition. Again, the 1,4 is a matter of resonance structures, where all we're doing is we've got our 3 p orbitals in a row like that, and so we can have our resonance structure move it from that positive over here, but if that positive goes here, then our double bond goes here. Okay, any questions? Now, it doesn't matter what kind of structure you have, I mean, it's gonna be like this. If it's, now, the thing is that you have to realize is, let's say that it's not symmetrical. Well, then you would do it, you'd have 4 different answers, wouldn't you? Possibly, unless some are the same. So we could have 4 different answers like we did in, hold on, which one was that? Show, let's go over here. 'Cause okay, like we did in this worked example here. In this one, it was not symmetrical. And so in this one, when we're looking at it, what do we have? Well, we still have, again, remember we have 1, 2, 3, 4, because now we're going this way. Why are we going this way? Because we've got to do the conjugation. So when we're doing the conjugation, we can go it that way, and when we're looking at it, we can have this one where we're going to put the hydrogen, and then for the 1,2, we'll put the Cl here, okay? For the 1,4, what do? Well, we're going to put the hydrogen here. Remember that it's a resonance structure, so this gets moved up here, and on our 4 position is where we end up with our chloro group. So we're shifting that double bond up 1. So we're shifting our double bond. So we're starting this double bond here for our 1,4. We always put our hydrogen here, or our bromine, or whatever we're adding in. It can be a Br2, doesn't matter. But anyway, and that, for the 1,2, this remains the same as we see here. And you put 1 here and then the Cl here, the hydrogen here and the Cl here. In this example, or 2 bromines in there. 2 chlorines, or whatever this is. Okay, but on the 1,4, remember you're going to have to put 1 here and 1 here. Okay, 1,2, you put 1 here and 1 here. 1 here, like the hydrogen and the chloro group. 1,4, 1 here with the bromo or the chloro here. Then on the 1,4, you move your double bond. Now for this other one, we could just as easily start here and go 1, 2, 3, 4, couldn't we? Okay, this is not a symmetrical molecule. And so on that one, we would also have that, where we would look at it, and we would, in this case, we go 1, 2. So our hydrogen would go here, and our chloro group would go here, and that would give us our 1, 2. And then our 1,4, our hydrogen would go here, and our chloro group would go here, and we'd have a double bond here. And that's kind of shown with this resonance form. In other words, where this positive charge is where the chloro group would go. This is 1, 2, this is 1, 4. In this case, these 2 are the same. You just flip them and they're the same. And so the 1, 2 and the 1, 4 starting on this end produce the same one. So that's why we have 3 products. Is that clearing it up just a little bit? Again, go 1, 1, 2, 3, 4. Number them, 1, 2, 3, 4. Then put the hydrogen on the 1, the chloro on the 2, the hydrogen on the 1, the chloro on the 4, but on the that one, move your double bond by 1. Okay?
So it's you always just move the bond within one?
Just for the 1, 4, yeah. On the 1, 4, you'll just move that bond up 1 and put the chloro on the number 4. Or the bromo, or the, whatever it is, iota, or whatever it is. Does that help clear that one up, I hope, some? I know that I was looking, and the carbocation is just exactly like it's shown. It'll be on the number 2 or on the number 4, and if it's on the number 4, the double bond will have been shifted. We're now on ultraviolet spectroscopy. Of course, I like spectroscopy, so you're stuck with us. I had to expand it out a little. I hope you don't mind, but I always like to expand some things out just a little bit, maybe make it a little bit more interesting, or maybe not. But anyway, when we're looking at UV spectroscopy, again, we said that we're looking at the molecular structure of the conjugated compounds. If we can get a sample that has a UV spectrum in it, it means it must be conjugated. Okay, as far as organics go, it's purely organics. Now we're not talking about the transition metals with those D to D star transitions. Okay, again, it is the one that will help us know we have a conjugated system. You think that would be important? It could be, couldn't it? So when we're looking at it, it's not as widely used as these others, but it does let us know that we have conjugation and gives us some idea about the conjugation as well. So, what happened? Okay, so when we're going back, the mass spec is the molecular size and formula. The IR is the functional groups. NMR gives us the carbon-hydrogen framework. But UV visible tells us something about the conjugated system. So when we're looking at it from where that wavelength is, we can get an idea of whether, you might know that there's 3 double bonds in there. Well, and it's a fairly large molecule. Well, if it's shifted a little bit in the UV range, depending on how much it's shifted to a lower energy, in other words, going towards the visible region, will tell us whether it's in conjugation or not, or could help. Now, whether it's 2 of them or 3 of them, that can matter too. So in that respect, it can be important. So let's look at it. This is just going back to the region of the electromagnetic spectrum. And what we see is that we have the energy, the ultraviolet is the UV that they're talking about. And it's normally, we don't go through all of this. We just say 200 to 400 nanometers. That's sure a lot better than 2 times 10 to the 7 meters, okay? So, well, you'll just hear it as 200 to 400 nanometers, and that's talking about the wavelength, okay? Now, right next to it is the visible region. Notice it's lower energy. We're going to talk about that in a minute. But most organics, if they're conjugated, or a lot of them, are going to fall in this region. If they have a lot of conjugation, they can move on up to the visible region. Now, what happens in this region? Well, what happens is that we have an electron that will shift up to a higher energy level. Okay, that's what happens in it. Okay, now let's think about what happens in all the rest of them. What happens in mass spec? Well, we bombard it, we form a cation radical, and everything fragments. Okay, and that's pretty much in a nutshell. In IR, we have all those nice molecular motions. Maybe we should do some exercises this morning. Anyone want to do some real quick, yeah, okay, so we'll do real quick stretching here. Okay, that reminds us what's going on in the IR. Okay, and in NMR, we do what? We do the flipping, and then it gradually successes on back. We flip our nucleus around in that, and then it goes on back. Yeah, we can do that, can't we? I like that. that. All right, now on this one, you wanna get up and jump, I mean, on this one, we're gonna jump up, I can't jump, so anyway, anyone wanna jump? We're gonna jump up, and we're promoting our electron up, okay, to a higher energy level. Okay, go for it. All right, so pretend like you're jumping. All right, we got it. All right, so anyway, we're gonna call it, so we're gonna promote from a lower energy to a higher energy, and we're gonna call the pi electron is gonna shift from the highest occupied molecular orbital, which we call it the HOMO, and it's gonna shift up to the LUMO, which is the lowest unoccupied molecular orbital. And we call this a pi to pi star transition, okay? So how's it look? Well, this is what it looks like. Here's our ground state electronic configuration. And so what happens is that if we hit it with UV irradiation, it has enough energy. Heat won't do this, by the way. It takes the energy of light to do this. It will promote this electron from here up to here, okay? Now really that should go up, not down, but anyway, it's just showing it's that one, I guess. And so that is what happens. So this is what goes on in UV when what happens. It'll go up to the excited state. And if you were to take advanced organic, we talk more about this, okay? Because it is a main feature of paracyclic reactions. In fact, I just finished teaching it and one of the students said, why didn't we learn that when we were, what we learned there? And I said, we don't have time. So anyway, but it makes things a lot more clear as far as some reactions that go on. But what you have to know is that it's just simply promoting, light will promote it up to the LUMO, the lowest unoccupied molecular orbital. So for a 1,3-butadiene, this happens at 217, which is right there in our UV range, okay? It will absorb that wavelength of light and get promoted up to the lowest unoccupied molecular orbital, which has now become the HOMO, right? All right, the highest occupied molecular orbital. In other words, it shifts it. All right, so here's a typical UV spectrum. It has more broadening. It has to do with just the molecule and what's going on in it. And the typical plot for the UV range is from 200 to 400. Now, a lot of times we have solvent issues that absorb in here or cause problems in here. And but the top of that, the highest energy is called the lambda max, and in this case it's 217 nanometers, but it varies with compound. And this absorbance is just simply the log of the intensity of light that we shine with nothing there, divided by the intensity of light that's transmitted, okay? So if it goes through a sample and it absorbs some of that light, then it's going to be less, isn't it? And the more it absorbs, if you put numbers in here, the more it absorbs, the lower this gets and the larger that gets when you do your math, okay? Now, the main reason that we use it is, number one, there's a whole bunch of Woodward rules, and they talk about what to add for this and what to subtract for this and all this other stuff. But we generally don't do that too much. But the main thing we use it for nowadays is characterization of the sample. In other words, if we know where its lambda max is, a lot of times that would be reported in literature and stuff. And that's like further characterization of the sample. But the main thing is for quantitation when we're looking at things, okay? We can use it for quantitation or just detection. We can also say detection. So what we see is that the absorbance for a particular compound in a specific solvent at a specified wavelength is directly proportional to its concentration. Wow, what in the world does that mean? Well, that means this. Okay, this is red dye 40. And see all the conjugation in there? Double bond, single bond, double bond. I'm going to go all the way around there, all the way up. That actually puts it up to the visible region because there's so much conjugation. Okay, I didn't do a UV one. This actually, when we're doing it, has a lambda max at 400.5 nanometers, which is in our visible region, which is 400 to 800 nanometers, okay? But what we did in this is that we made a calibration curve. And so we did 0.01 grams per liter, 0.2, 0.25, and 5. And notice how the absorbance goes up proportionately. Okay? That's what this is saying. Okay? And there comes a point when it no longer holds, but then you just make sure that you're down in the region where you get a nice linear relationship. So, Beer's law, this is Beer's law. It relates this out. How many of you remember Beer's law? If you didn't have analytical, how did you do it? Everyone in analytical should remember this one, okay? Beer's law says absorbance equals the molar absorptivity, and sometimes you see that as a little a, or you can see it as this. It says extinction coefficient. A lot of times you'll see it as a little a, times the concentration times the path length. Usually that's 1 centimeter. Or you did UV vis in 111 and 112, didn't you? In your lab? Those little ones like this, those little cuvettes, they had a 1 centimeter path length, okay? And so that's what that's talking about. In other words, they're 1 centimeter, they're shining of your sample in there. Okay, so this is what you get, and so then you can take an unknown, and let's say that your unknown absorbance units were 1.78 or something like that. Then you'd go from here over to here, and you'd see that it was somewhere around a 0.04 grams per liter concentration. Now you can do it moles per liter, you can do it other ways. And of course you can always just use your equation so that you don't, because it's hard to figure it out on the graph. But this is what we can use it for in organic chemistry is a lot, is for concentration determinations. We also use it just in detectors to see when a peak's coming through, like you did with HPLC. Remember your HPLC lab? Did it work? I know there was some high performance liquid chromatography last semester. You did the fluorine and fluorinone. Yeah, did that work? You saw your peaks, right? Okay. So molar absorptivity is the amount of light absorbed that depends on the molecule. This is why we can't just go like we do in GC mass spec and kind of look at the areas under the curves and do concentration. We couldn't do it for flame ionization, but we could for GC mass spec. Molar absorptivity is the reason that if we were going to quantitate, we can't just look at the peak areas, okay? I think when you did your fluorine and fluorinone, you would have found that your peak areas weren't the same even for a 50-50 mixture. Does anyone remember that? No, they weren't. Trust me. And the reason is because one of them had a higher molar absorptivity than the other. Not all molar absorptivities are created equal. Some will absorb a lot of the light. Others will absorb, or that wavelength, others will absorb very little. Okay? And so you can't, so you have to do calibration curves or know the extinction coefficient, the molar absorptivity. So what we do is that we usually don't put these units, liters per mole centimeter, but that's what it is. And we just rearrange Beer's law to solve for it. And so if we end up knowing all of this, we can solve and get our molar absorptivity for that compound. Okay? So beta carotene, orange and carrots, and its molar absorptivity is 138,000 liters per mole per centimeter. And so if it's placed in a 1 centimeter path length, again, there's our calculation, our Beer's law rewritten. And we get an absorbance reading of 0.37, and then we take it, and what we see centimeters cancel out, this invert and multiply, and we end up with 2.7 times 10 to the minus 6 moles per liter. That is our concentration. So if we know our molar absorptivity, we can get our concentration from that. Otherwise, we have to go and do those graphs and figure out our molar absorptivity. Okay. Now, gotta put green chemistry in where I can, okay? So we're gonna talk about green chemistry because UV is one of the methods that's very often used if they're gonna do some green chemistry in industry to monitor reactions. There's other things like they can use heat and different things, but this actually relates to what's the Pope principle of green chemistry, which is real-time analysis for pollution prevention. So what exactly is that? Well, it means that if you're doing a process, okay, and let's say that you put in so much of something and you're letting it react, okay? Now, let's say that if it reacts so long, it'll make your product for so long, and then all of a sudden it'll start going and making another product. Well, wouldn't you like to know when it is finished making your product that you're wanting? Otherwise, what happens? If it goes too long, you get this waste to get rid of. If it doesn't go long enough, you got your reactants to get rid of. So you want to be able to maximize your product, okay? And so a lot of times UV is used for that. So that's one way in which it can be used. And they have them now where they actually will be doing in line. And it'll go around this line, and then various places within this reaction, there'll be a sensor there which will tell it everything's okay or not, okay? And so it's done to detect the completion of a reaction, to prevent waste, and also to detect changes in the process or product before a major incident, such as an explosion, could occur, okay? So right now the US FDA is really pushing the pharmaceutical industry. Pharmaceutical industry is really embracing green chemistry at this moment. At one time said, hey, we don't really make that much, we're not a big polluter like, you know, some of the major chemicals that are out there are, and we just do these smaller type batches, but they have really come a long way, and they are, the FDA and everyone's kind of pushing them. And pharmaceuticals, they're finding that they're making more money because after all, they don't have as much waste to dispose of. They're figuring out more efficient, greener methods, so it's more friendly, more to the environment and also to its workers. Less explosions, that's always good, right? And so this is one good use of UV. It has a lot of good uses, but of UV spectroscopy. So now it's your turn. Who needs a calculator? I'll go get some. Somebody bring it out. One. Okay, I'll go get a few. Anyone else need a calculator? Yes, we can share one. Oh, that's okay. That's okay. I'll be right back. I forgot to bring something with me. I forgot to bring the worksheet for chapter 14, so I'll be right back with it.
Concentration?
How are we supposed to figure out the molar absorptivity? Like we have two factors that give you the molar.
I thought
that we have everything we need, right?
I think we have everything we need.
Oh wait, there it is, never mind.
Can we just plug it into this? I think it's about 8 divided by E times L.
Hey, how you guys doing? I'm gonna warn you, I'm pretty sure I'll have some, at least one, if not two, of these on the test in the various forms. I haven't done the test recently, but I know I'll have some. Because I don't want anyone getting out of Union's chemistries not knowing how to use Beer's Law. I mean, that is a major use in chemistry. And I think that everyone needs to be able to do this, okay? So let's see if you got it. How many of you got it? 1.47 times 10 to the minus fifth? Okay. Yeah, no Beer's Law, it won't be given to you. That's something that you just really need to know. So be sure you know Beer's Law. Okay, so now interpreting UV spectra of the effect of conjugation. We talked about the pi to pi excitation, and that amount of conjugation will make a big significance over the influence of the wavelength. So what are we saying here? The lambda max is again where the wavelength absorbance for a compound is the greatest, and what we know is that as we get more conjugation, the difference between the HOMO and LUMO, in other words, the extent of the conjugation will cause it'll be lower energy required, okay? So lambda max increases as conjugation increases, which means that we have lower energy. A higher wavelength is lower energy, right? Higher wavelength, lower energy. So when we're looking at this, let's just go on to the next one. I think it shows it better than just reading all of this. Okay, so this is just showing how much conjugation is here. So this is double bond, then single bond, then double bond, then single bond. If there's 3 of those, then this is what it looks like. If there's 4, notice that the lambda max going more towards lower energy, it's here. If there's 5 of them, it's even lower energy. So the more conjugation, the lower the energy. This is just showing some numbers to it. Now benzene's a little weird. It's at 203. So it's there, but it's not really where you'd expect it to be. But for example, here's the 135 hexatriene, it's 258, but when we add one more unit of conjugation, it's all the way up to 290. So we can see that as we add conjugation, it increases the wavelength, which means it's lower energy. So determine if the following compound exhibits ultraviolet absorptions in the 200 to 400 nanometer range. If you think it does, raise up one finger. If you think it doesn't, raise up 2. What is it that we have to determine? Conjugation. Is this conjugated?
Yes.
Yeah, we have a double bond, a single bond, a double bond, a single bond, a double bond. This is conjugated, so yes, it would. Okay, let's look at this next, at this problem. Which of the following compounds would you expect to show UV absorptions? Would A,
No.
B,
Yes.
C?
No.
Okay, what is C? Okay, well, we're looking at C, we have a double bond. We come down here and a C triple bond in. Is it conjugated? This gets people every time. Remember, CN is a triple bond, okay? It's a nitride. How about D?
Yes.
E?
Yes.
We just,
We just looked at that one, yeah. And F?
Yes.
So answer is all but A. Okay. Okay. Well, let's just kind of look at vision here, doing this. Pigmentation of compounds are caused by the chemical structures and the human perception of light. The visible region now is lower energy than the UV region. It's here, but it's adjacent, directly adjacent to the UV region. It's from 400 to 800 nanometers. And this is just so you can see it a little bit better. I don't think I did that on your student thing. I figured you could see it. Okay, so here's our beta carotene. Look at how much conjugation that is. All the way from here, this is included. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I said if you get something that's colored, you know it has a lot of conjugation. As long as we're talking a purely organic thing. Okay, its lambda max is here. It's at 455. It's orange. Why? Okay, well, it's in the visible region. This is what we see. This is what its UV visible looks like. UV visible goes from usually from 200 to 800. Obviously, there's not anything over here. And here's its lambda max, its highest absorbance at 455. So this region here, we're seeing orange. Why are we seeing orange? Well, what we're going to see is this is actually white light minus blue, and that's why we see the yellow-orange. We have this nice color complementary thing there. And so if we're seeing orange, then that means that we must be taking that out. Okay, that's how this works. So it's the orange is because we have the white light minus the blue. In other words, whatever we take out, it's the opposite, is what we see. So, beta carotene helps us with our vision. Eat lots of carrots. Anyway, what we start off with is beta carotene. And what happens is that it's converted to this 11-cis retinol. It'll go via vitamin A. So this gets cut off here. We form the alcohol here. And then that will, through some chemical reactions, end up with this being 11-cis retinol. In other words, between the 11 and the 12 bond it's cis. Okay? Where we start off, everything's trans. Now, human vision, I don't know if you studied this in biology, you probably did, so, but anyway, it's because of our light-sensitive receptor cells in the retina of the eye, called the rods and cones. Everyone knows about rods and cones. 3 million rods in dim light, 100 million cones in bright light. In the rod cells, what happens is the 11-cis retinol is converted to rhodopsin. Now, this is what's interesting to me. When light strikes, it converts to metarhodopsin. In other words, light strikes and this cis goes to trans. Takes 200 femtoseconds. That's fast, right? That's why we see things immediately. Without that, without the light present, it would take 1,100 years for that to happen. Okay? Hopefully you found that halfway interesting. And this causes the nerve impulse to be sent through the optic nerve to the brain, and it's perceived as vision. Get the summary, work a problem. Explain why 2,3-diterbutyl 1,3-butadiene does not undergo the Diels-Alder reaction. Why does it not undergo the Diels-Alder reaction? Strain, yeah. Is that what you were saying too? Yeah, these are going to come in way too close for it to be able to undergo a Diels-Alder reaction when we do it. Okay, get this. These are just the Woodward rules. I had to. When you're figuring out where your UV visible spectrum is, there's all these things that you add or subtract, add things for in order to figure out where exactly it should go. extra, it's on photolithography. Photolithography, I guess, it's just revolutionized computers. 50 years ago, if you wanted to own a computer, you would pay $150,000 for 60 megabytes of RAM. You think, and cost of living's gone up, so $150,000 was worth a lot more then than it is now. Okay, and it'd be the size of a small desk. Okay, so today we can buy it for a lot less. Most people don't even mess with 60 megabytes of RAM anymore. And it could fit in your shirt pocket. And the difference is because of a process called photolithography. It's amazing how organic chemistry is everywhere, and you never realize it, right? Okay. So what happens? Well, I can go through all of this, or I can just show you the reaction thing. So let's just go to that. This is just showing circuitry, and this is it. They start with the silicone layer. They put a silicone dioxide layer on top of it, and on top of that they put something called resist. The resist is an organic molecule. And the organic molecule, then they mask it, and they expose it to light. And when they expose it to light, it makes what is hit by the light where it will wash away. Okay? What isn't hit by the light remains. So then they will etch it, and then they add some more stuff to it, and they get rid of the resist, and now you have what you need for an integrated circuit chip. And again, the resist is an organic molecule. And it's based on two, and resist, it's for this chip manufacturer, it's based on a two-component diazoquinone Novolac system. The Novolac is soft, relatively low molecular weight polymer. It's made from methylphenol and formaldehyde, and the diazoquinone is a bicyclic two-ring molecule in this diazo group. Okay, and it's insoluble when fresh, but when exposed to the ultraviolet light, what happens is that it breaks down. The diazoquinone compound here, when exposed to light and water, will turn into this carboxylic acid and nitrogen gas, which then can very easily be removed. Okay? And so that's how it works. All right, I'm going to hand out this worksheet. This worksheet is a worksheet that's kind of a review, not just for going over what we've hit today, because if we go into what our reactions are that we've covered for this, our summary of reactions, where is it? We only see that there are only two reactions, the electrophilic addition and the Diels-Alder. That's it. But this here is to be used as a review for what we